My name is Fanni Nedényi, and the title of my talk is Limit Theorems for the Aggregation of Random Coefficient INAR 1 Processes. Integer-valued autoregressive processes of order 1, or shortly INAR 1 processes, are very well applicable to model the size of a population. Then, for any k, xk is the size of the case generation, whose individuals are either offsprings of the previous generation's xk-1 individuals, or they are immigrants who arrive to the population at time k. So, to get xk, we add up the offsprings of the first individual of the previous generation, xk1, those of the second, xk2, and so on, and finally the innovation, epsilon k. We assume that x0, all the offspring and innovation variables are independent of each other, the offsprings are Bernoulli distributed with some fixed parameter alpha, and the innovation has Poisson lambda distribution. And thus, we can also represent xk as the alpha thinning of xk-1 plus the innovation. Moreover, we choose the distribution of x0 as Poisson with parameter lambda over 1 minus alpha. Then the process is stationary as well. Count processes, including INAR 1 processes, are widely applicable, for example, in medicine, epidemiology, insurance, and meteorology. Let us consider our INAR 1 process, which is in the first row here. Studying the sums of this process, which in our case represents the number of all individuals that have lived in the population up to a certain point, is a fundamental question. We have independent copies of this process in all the other rows, meaning that the processes all behave the same way and they are independent of each other. This means that we consider many independent populations and how the number of individuals that have lived in the first capital N populations until a certain time small n behaves as these parameters converge to infinity in some manner. So, we are interested in the limit behavior of this sum here. We can examine the case when capital N, the number of populations, tends to infinity, and then the time parameter n tends to infinity, vice versa, or when they both converge to infinity at the same time with some rate. We are interested in what kind of centering to apply, how to scale the center sums, and what limit distributions we achieve. Here, all of these processes share the same dynamics and have the exact same thinning parameter alpha. A question naturally arises. Could these remain similar by sharing the same dynamics but having different thinning parameters? For this purpose, we consider a random coefficient INAR 1 process. Here, the main form of the process is the same, but instead of having a deterministic alpha parameter, it is a random variable with values between 0 and 1 with a certain density function. It is psi x times 1 minus x to the beta, where x is between 0 and 1, and beta has to be bigger than minus 1, so that this actually is a density function. The function psi is integrable, and it has a limit at 1, which is represented by psi 1. Note that the density function has a parameter beta, which will have an important role later on. Then all the previous assumptions, so that x0, the offsprings and the innovations are all independent of each other, the offsprings have Bernoulli alpha distribution and the innovation has Poisson lambda distribution, has to hold conditionally on alpha. Also, conditionally on alpha, x0 is going to be chosen to have a Poisson distribution with parameter lambda over 1 minus alpha, so that, again, the process is going to be stationary. Similar mixing distributions, which is the distribution of alpha, have been applied before. For the aggregation of random coefficient AR1 processes, The Nobel Prize-winning Granger applied the square root of a beta distribution, while Piripauskaite, Puplinskaite, and Surgaidis, in many papers of theirs, used the same density function that we do here. That is where we get the idea for this density function. First, I am going to show you limit theorems corresponding to the case when first n, the time parameter, converges to infinity, and then capital N, the number of populations that we consider, converges to infinity. Thus, these are called iterated limit theorems. Here, we center with the conditional expectation, which actually always exists. Instead of the time parameter n here in the sum, we apply the whole part of nt so that we achieve a process s tilde instead of just the sum. Note that we have different results for different ranges of beta, which is a parameter of the density function of the random coefficient. These are here in the table. This table contains the scaling sequences with small n and capital N, and the limit processes as well. Among these limits is y variable is a stable random variable, and this sigma here is just some constant. So for example, the second column, this one, means that for beta equals 1, the finite dimensional distributions of the process S tilde scaled by the square root of n times capital N times the logarithm of n converge to those of a standard Brownian motion multiplied by a constant. All of the limit theorems in this talk are understood in the same sense, the convergence of the finite dimensional distributions. On this slide, I'm showing you the iterated limit theorems when first capital N, the number of populations, converges to infinity, and then small n, which is the time parameter, converges to infinity. So similarly, we have different results for different ranges of beta. Here, v is just another stable random variable, w is a normally distributed random variable, and b, 1 minus beta half, is a fractional Brownian motion with parameter 1 minus beta half. Note that the scaling sequences increase as beta decreases. This happens because the bigger beta is, the higher moments of xk exist, which are the variables in the random coefficient INAR process. With these results, the list of iterated limit theorems for the process S tilde, so when we center with the conditional expectation, is complete. Lastly, I would like to show you the results when we center by the expectation instead of the conditional expectation. Unlike the latter, this only exists when beta is bigger than 0. We can derive this aggregate from the previous one, S tilde, as they only differ by the sum of the differences of the two types of expectations. Since the processes xj are stationary, we can reduce this problem to the convergence of a sum of these IID random variables. We prove that the random variable lambda over 1 minus alpha is in the domain of attraction of a stable distribution for beta between 0 and 1, and the normal one for beta bigger than 1. These are what we see here. Our newest result is that for beta equals 1, it is still in the domain of attraction of a normal distribution. Here we only know that a scaling sequence exists with some asymptotic property that is presented here, but we have not been able to specify the sequence itself. Any suggestion on this would be appreciated. Note that the list of iterated limit theorems for the aggregate process X is complete. Here are a few references. Most of the iterated limit theorems are given in the first paper, except when beta equals 1. That case was handled in the third paper, which also contained the corresponding case for random coefficient autoregressive processes of order 1. In the second paper, which is about to be published, simultaneous limit theorems are presented. I did not have time for these in this short talk. The list of simultaneous limit theorems is not complete yet. Some remain for future work. The paper by Piripauskaite and Surgaidis about the aggregation of random coefficient autoregressive processes of order 1 was a very important motivation for our work. Thank you very much for your attention.